Hello, it's Stat134, lecture 33. Last time we finished section 5.4, including the convolution formula for the ratio. Let's review that. For a ratio, z is y over x, where x and y are positive independent. We can write y is equal to zx, so we're sort of interpreting z as the slope of the line y equals zx. And the probability that z is in dz is a little wedge shown in the light green here. And in particular, the little parallelepiped region in the darker green there is the probability that z is in dz and x is in dx. And so that probability is the volume under our joint distribution of x and y over this parallelepiped. So that volume is approximated by the height of the joint distribution at the point x is zx times the area of that parallelepiped, which is, so we have dx and dy is x dz, because you can see that the difference in y, for the top line y is z plus dzx, and for the bottom line it's y is zx. So that change in y is in fact x dx, x dz I mean. So we get the probability that z is in dz. So this is basically a sum of all of these little parallelepipeds as x goes from 0 to infinity. And so we can write this out. That gives us our convolution formula for f of z, the integral from 0 to infinity, f of x, f of zx, x dx. So today we're going to review some student explanations from the concept test from last time, and we're going to start in chapter 6, section 6.1. Please read on your own. There's nothing really new there. We've done a lot of conditional distributions before the midterm. For the discrete case, what I want to spend our time on is section 6.2, which has new material including the conditional expectation and the rule of average conditional expectations. So the concept test from last time, U is standard uniform, V is also standard uniform, and they're independent. The density for Y is U over V, where Y is between 0 and 1 is which of the following. So I let you guys discuss for a minute, and you can remember the solution that I went over last time. I won't go over that again, but reading some other students' solutions I think is quite interesting. So one student says, draw a pair of lines that are near each other, and I find that the area they cover is 0.5 dz. So that's very nice. So just remember that we're looking inside of a box, a 0, 1, 0, 1 box here. And so the area of this wedge over here, the area of this wedge is the area below the top line of that triangle minus the area below the bottom line, that triangle, right? So the area of the top triangle is 1/2 height. The height's y plus dy, and the width is 1. So that's right. And then the area of the bottom triangle is 1/2 y times 1. So that difference is 1/2 dy, and hence dy, f of y must be 1/2. So that's very nice. Another student uses what's called the CDF method. So he looks at the probability that y is less than y and writes that's equivalent to the probability that u is less than vy. So the line u equals vy, I've sort of drawn that line and I'm looking for the volume, for the area underneath it. But if I only go to v is 1, then that area, so that the area of that shaded region there is 1/2 times the height is y and the length is 1, so it's 1/2 y, and you take the derivative of that and you get 1/2, and that's the density. So that's very nice. Another student basically gave the same solution I did using the convolution formula. The PDFs of u and v are 1, so f of v is 1, f of u of y v is 1. Use the convolution formula to find f of y, which is the integral from 0 to 1 of 1 times 1 v dv, which is 1/2. Of course, Mike is always right. And once one person didn't do the integral from 0 to 1, but instead did it from 0 to y, and that reminded me of the convolution formula for the sum. So just make sure that you keep your convolution formulas straight. Okay, so conditional expectation, remember Bayes' rule. And so just let's just review how to find probability that t is 3 given that s is 7 given a joint distribution. So we find that that's 0.75. And so I gave you guys some problems to practice. And here the expectation of t is, so t takes the values 3 and 4. And the probability, to find the probabilities that t takes those values, you have to look in the marginal of t. And for the conditional expectation, which is the third one here, t takes the same values, 3 and 4, but now instead of probability that t is t, you need probability that t is t given s is 7. So you use conditional probabilities there. And so we get 3.25. So gave you another one to practice here. You all did this great. And so what we see here is that the expectation of t given s is 7, s is 6, s is 5, this is a function of s. So that's a little funny, but these conditional expectations are functions of what you're conditioning on. So I don't know, I came up with this way of trying to visualize what these conditional expectations are. So imagine I'm just going to multiply all the cells in my table by 10. So my sum is 10. So I'm just imagining that I have 10 data points, and I'm going to make a scatter point, a scatter diagram. So I have 3 points that are with s is 7 and t is 3. I have 1 point that's s of 7, t is 4. And and I've drawn an x to show where the conditional expectation is with s is 7. So of course it's some number between 3 and 4, leaning more closely to 3 because we weigh the 3 more than we weigh the 4, right? So it's 3 1/4 versus 3 1/2 for when s is 6 and s is 5. So it's kind of a visual way of seeing this. But the main points here is that the expectation of t given s is a function of s. The expectation of t given s is a random variable, and so it has an expectation. And so we're going to explore that. So let's write this function of s as g of s. So g of s is the expectation of t given s. So g of 7 is 3.25, g of 6 is 3.5, g of 5 is 3.5, and so on. And we know the formula for expectation of a function of s. So it's just summing over all the values of s, g of s times the probability that s is s. And lo and behold, you get exactly 3.4, which is the expectation of t. So this is the property of iterating expectations. The expectation of the conditional expectation is the expectation of t. So, and it's kind of intuitive. If you have a class that's 2/3 girls and 1/3 boys, and the girls weigh 100 pounds and the boys weigh 200 pounds, then on average, the weight of the class should be 2/3 times 100 plus 1/3 times 200. So it's pretty intuitive, right? And so we call this formally the rule of average conditional expectations. And we'll deal with x being continuous in the next section, but right now it's discrete. Okay, so you can look at the end of these notes for a formal proof of the law of iterated expectations. It's just algebra. But we did an example. You have 8 transistors of type 1, distributed exponential 1/100, 4 transistors of type 2, exponential 1/200. T is the lifetime of a randomly picked transistor. Find the expectation of T. So let X be the type of transistor. Expectation of T is expectation of the expectation of the conditional, expectation of the conditional expectation. And we can just write this out and we get 133.3. So it makes sense here. So the whole point is I may not know what the expectation of T is, but I do know what the conditional expectation is, because the conditional expectation, because the conditional distribution T given X has a distribution that I know, namely exponential 1/100 or 1/200. And I know the expectation of that distribution. So then we did a concept test. So let n have Poisson mu distribution. Suppose n is n, random variable, x follows binomial. Find the expectation of x. So we know that x given n is binomial np. So we know the conditional expectation. So the expectation of x given n is a random variable of n, so it's n, capital NP. So the iterated expectation is the expectation of n times p, which is just mu p, because remember the expectation of Poisson mu is mu. I just want to mention that if you try and write out this conditional expectation as a sum, using this definition, using this highlighted definition over here, it'll totally work for you. You can totally do it that way, but just notice that you're gonna have to rederive that the expectation of Poisson is mu, and somewhere in there you'll have the expectation of you'll have the sum of the probability that n is n, as n runs from like 1 to infinity is 1. So that infinite sum will drop out. And then we did a follow-up problem where now n was geometric p, and it was exactly the same argument, except now expectation of n is 1/p. So you get 1/p times p is 1. Great, so good job on this, and I'll see you next time.